Hey everyone, it's Dr. Calkins. So today, a little bit of lecture on week 11, chapter 15. Try to break this chapter up into two videos as well. One with acids and bases, and the other one with pH kinds of things. So week 11 is really about understanding acids, bases, and electrolytes in particular. So if you're an acid, we'd expect you to be sour. We'd expect you to have a low pH. Your tongue can recognize this pH on the sides of your tongue, so it makes your cheeks pucker when you eat a lemon that has citric acid. They can also produce hydrogen gas, and that's because they can dissolve metals. If they're high enough on the activity series, we'll see that in our next chapter. So it's important to know what acids are, because bases are basically the opposite in the sense of their definition. So again, these will also turn pH paper red. So let's look at a base and how it's different. A base is going to be bitter, and your tongue can recognize that bitter taste on the back. When that muscle is contracted, you get a gag reflex. A lot of medicines are bitter because of their amines and amides in particular. So a lot of times you see the little yuck sign with the slash through it, and that's because most bitter pills are bad for the stomach. It's going to neutralize the stomach. Oftentimes they're buffered to minimize that effect. But if you're a low pH for an acid, you'd expect the opposite here. So you're going to have a high pH. It's basically lower than 7 for acids, higher than 7 for bases. See that in another lecture as well. And what's most important about these is they're going to be slippery. So things like bleach, detergent, soap, slippery because they're very basic, good at cleaning the skin because that's strong base. And again, if they're turning pH paper red for an acid, you'd expect this to turn pH paper kind of a blue, litmus paper blue. And what's nice about acids and bases is these are just categories of electrolytes, which you can find in Gatorade. Because all of these can make ions, and our job in all of these is who is strong as an acid, as a base, as an electrolyte, who is weak, and who is nothing at all, so a non-electrolyte. So when we think about those three categories, think about them for all three subtopics, acids, bases, and electrolytes. To be strong is kind of like in a scary movie. The villain is chasing you through the woods. If you're strong, you're going to split apart into positive and negative ions. So this is going to happen 100% of the time. If you're strong as an acid, strong as a base, strong as an electrolyte, you're going to split apart into ions 100% of the time in that beaker. If you're weak, you're really just going to stay together and maybe split apart a little bit, about 1% of the time maybe. So most of the time you're together as this positive negative molecule, whether that's through Lewis dot structures or actual ions, just depends. But if you're weak in that scary movie kind of analogy, what's happening is you're hiding in the bushes with your friend, hoping that the bad guy doesn't find you, so these, again, stick together. These are very important for the body because we need weak electrolytes or weak acids and bases ready and waiting, so that when we eat food or eat medications, we can neutralize them with available acids and bases. The problem with strong is they'd already be separated, they'd already be used up. Non-electrolytes, typically gas molecules, because they're nonpolar. Most organics, except organic acids. So things like alcohol, when you drink a beer after, the stereotypical dad drinks a beer after pushing going to grass. Do you think that beer is really going to help? Might numb the pain from all that physical exercise, but what it's not going to do is replace those positive and negative ions and those strong electrolytes through his sweat that they're losing. So drinking a soda with lots of sugar, the same issue. Those organics cannot split into ions. They can't help muscle contraction, because really what we have in our body, as we look at our muscles, so here's an imaginary bicep. We need electricity to be carried across that muscle. So if electricity or current through our nerves goes through that muscle, we need a way for it to go across those muscle strands. The only way for that to be possible is to have positive and negative ions to allow the electrons to flow just like electricity, but through that tissue. So that's why our body wants strong electrolytes like Na plus and K plus, so that we can conduct electricity across our muscles. Unfortunately, if we have non-electrolytes, they don't make any ions, so as we sweat and lose them, now this muscle contraction can't be completed and we get, say, a Charlie horse. Our muscle cramps, it gets frozen because we down some power lines. And it's all that idea of understanding acids, bases, and how they function along with the things that don't function. Another way to think about it is a light bulb. You have this cartoon light bulb. You have electrons in and electrons out, and the light bulb glows. But if this wire was separated in a, say, beaker, and we were allowed to bring electrons in, could they be carried across the beaker? So sure, they might light up this bulb, but if we have a separate bulb over here, would this one light up at all? And that would depend on what's in the solution. If there's positives and negatives, in the sense of strong electrolytes, strong acids and bases, this light bulb would be very bright. If it's more of a mixture of positive and negative that don't really separate at all, now it might just barely glow. But if you throw sugar or water in here at all, it's going to go out. And it's not going to light up at all. So that's the issue that we have understanding acids, bases, and electrolytes. They're all interrelated. Strong separates, weak doesn't, none doesn't at all. So again, when we say weak doesn't, it doesn't 99% of the time. Only does it when it has to. So historically, let's look at a few definitions and then talk about pH in a later video. So one of the first definitions was Arrhenius. And Arrhenius was kind of overlooked. He thought of these ideas way too early before protons, neutrons, electrons were discovered, but his acid definition was basically H+. If you have H+ ions, you can be an acid. And for a base, you can have OH- hydroxide ions. And the reason that this was so easy of an idea for him to think about is that's just water, HOH, or in our case, H2O. So here's our acid, here's our base. So it was one of the earliest definitions of how to think about acids and bases. But just like one of the first cell phones, it wasn't great, so Brunstad and Lowry came along and said, let's make it a little bit less specific. So they said, sure, H is great, so we'll call it a donor of H+. But for a base, he said, or at least they said, let's be an H+ acceptor. The problem with hydroxide is hydroxide can accept an H+, and when that happens, it makes water. But even water can accept an H+ and become hydronium. Even ammonia can accept H+ and become ammonia. So for these reasons here, we had to expand the definition for what it means to be a base. And that's where our textbook stops, and that's where we should stop, but just a hint for those that are going to go a little further into, say, Gen Chem. There is one that's more important, in my opinion, and that's Lewis. Same guy that gave us Lewis dot structures. His definition didn't, or at least wasn't specific for anything atom-wise. So H+ out the window, hydroxide out the window. He said it's all about electrons because he did Lewis dot structures with electrons. He said if you're an electron pair acceptor, you're going to be a Lewis acid. If you're an electron pair donor, you're going to be a base. So in the sense of ammonia up here, it's an electron pair donor. Amines are bases, ammonia is a base. H+ is an electron pair acceptor, and we make ammonia. So it's just another way of thinking about the same thing. Water can donate its electron pairs to H+ acid and make hydronium, just like ammonia did for ammonia. And just like up here, hydroxide can donate an electron pair to H+ and make water. So all of those are tied together through electrons, really. It's just that Arrhenius didn't know electrons existed. Brunstad and Lowry weren't quite that idea yet. And I think as we talk more about acids, we'll talk about how to recognize acids in another video along with pH. So this gives you a good foundation for what's the difference between acids and bases to get you started on the homework.